Hello and welcome back to the Shellcode Obfuscation series. This is Flipping the Script. In this installment, we're going to take a look at flipping things around, putting our bytes in reverse order to see if that'll help us with obfuscation. So let's go ahead and take a look at some example code to see what I'm talking about. So what we have here is our shellcode that we're pretty familiar with now, FC4883E4 ends with FFD5. So we've just got a list that contains our shellcode bytes. And what we're doing is we're printing out that list, but we're using this here. This colon colon -1 says reverse the output. So it's going to print this in reverse. And if we run that, we can see it's in reverse. So we have FC4883E4 ending with FFD5, exactly what we're used to. And this is the C program that we would use to actually run that payload. So here we have our bytes in reverse byte order. You can see that this happens to be a different sized shellcode than some of the ones we're looking at, but it is interpreter shellcode. And what we have is an array that contains our shellcode in reverse byte order. So that means FC is going to be the last byte in the array, FC 4883E4. So now we're going to reverse our array. So here we've got a printf statement because defender is going to defender, and it actually will detect this program simply by doing this. The way it works, we've got a index variable called I. We're going to start at 0, and we are going to insert into shellcode index 0, and then we're going to call this reversed payload, size of reversed payload, which is going to be 562. So it's going to be 562 minus I, which is currently 0, minus 1. So we have to do minus 1 because we're in 0 index numbers here. So we need to shift to position 561 because when the array size is 562, that means we have possible indexes of 0 through 561. So into shellcode index 0, we're going to put in reversed payload entry 561, which is this here. And then we'll print out the output. And if we run it, FC4883E4 ends with FFD5. So it's exactly what we expected. And Defender does not detect anything. Now let's take a look at our next example. So the next example is going to be reverse byte order, but we're going to add a XOR in there. So we've got a random byte that we're going to generate. We've got our shellcode in reverse byte order, and then we're going to print out the output, and we're going to XOR each of the values with our XOR key. And this, of course, prints it out in reverse order. So again, very simple. Let's try that. So now it's going to print out our values. It's printing as integers, but again, this is the same thing. And we see that our XOR key is 232, and we've got our shellcode. So it looks like here, based on the size, I might have used a different interpreter .bin file. So now let's go ahead and take a look at that example in our C code. So we're doing a couple of different things here. I'm actually brute forcing the key here. So uh, let's walk you through what we have. We've got our bytes in reverse order. We know what our first byte is. We know that 252 is FC. We've looked at that before. So this is our first byte of shellcode. FC, we declare an empty array to store our shellcode. So what we're going to do here is figure out this last byte, which is this here, 128. We're going to read from our reversed payload array. We're going to grab the last byte, which is this here, and then we're going to brute the key. This isn't strictly necessary. This was just something to try out that I decided to include. So what I'm going to do is I'm going to pass it the first byte, what we know is our first byte, and the last byte that is in the array. So we know our first byte is 252. We know the last byte in the array is 128. And we're going to loop through 0 through 255, try zoring, and see if they match, if the result matches. If the result matches, that means that we've found our ZOR key, and we'll return that value. Once we have our ZOR key, then we're going to ZOR our payload. We're going to get back our plain text shellcode. Again, we've got a printf statement here because Defender was detecting this routine without detecting the shellcode. So we've put this in to throw Defender off. Now we're going to figure out each of our decoded bytes by reading from reversed payload, in this case, 598 minus I. In our first iteration, that'll be 0. So it'll be 598 minus 1 to shift us to the last position because we've got a 0 indexed array. Then we'll ZOR it with our ZOR key and store that value in shellcode index I, which is currently 0. So we're going to store FC or 252 in that array. And then we're going to run it and we're going to print out the output. So let's run that. You see you've got FC 4883 E4 ends with FFD5. So if you can't see that, you can see the bytes right here. FC 4883 E4. So that worked exactly as we expected it to. And if we test it out, Defender doesn't detect anything. So great. Let's look at the third example. So the third example is a little bit different. So in this example, what we're going to do is take our shellcode list. We're going to convert it into a hex string. And then we're going to replace any instance of a null byte, which would be 0x0. That's what 0x00 becomes when we run this command here. And we're going to replace any instance of 0x0 with a z. The z doesn't matter. It could be any character or any letter. I'm just going to use z as a placeholder, and we'll find out why in a minute. But let's look at the output. Reverse hex string. So now we have a string of our shellcode bytes, but now this is literally just a string and it's reversed. So you can see here 0xFC 0x84, and we can make this a little bit bigger so that you can see that. So we've got 0xFC, 0x84, 0x83, 0xe4, ends with FF in D5. So this is our list converted to a string and reversed. And any of our null bytes have been replaced with a Z. So let's take a look at why I did that. So in this last example, things are a little bit different. We now have this string that represents our shellcode in reverse with those null bytes converted to Z's. So now I'm going to create something called hex string, and I'm going to use the stirrev command, which will reverse the string. So this is going to get it back so it reads 0xfc, 0x84, and so on and so forth. We've got a new array that's going to store the results of our shellcode once we get done converting it. But to do that, we need to take a few steps. So I'm going to create an index variable that is equal to 0. We're going to call this pointer next token, which points to null. Then we first run if shellcode idx, so shellcode 0 equals stir to L, so that's a string to long. This is going to convert this into essentially a byte of shellcode. And then we're going to use stir toke underscore s. So this is string to token. So this is going to take our entire hex string. It's going to search for the uh, comma delimiter. And then we've got this null byte here, our null that we're pointing to. That is the reason that we used Z's, because it's looking for null bytes as the delimiter. So if we had 0x0 in here or 0x00, that would be a null byte. And then uh, string to token would think that that was a delimiter and would try to insert an empty value into our array. So in this case, we have Z's. And if it is able to convert it successfully, it means that the value that we had here was 0x FC, for instance, on the first instance. It was able to convert that to a long using the stir to L conversion. However, if it wasn't able to convert it successfully, that means it had to have been an invalid value. It wasn't a valid string representing a byte, right? So that means in our case, it has to be a Z. So if that's the case, we're going to insert a null byte at that index in the array. And when stir toke s was called, it actually trimmed this off of the list. So now the hex string is the hex string minus 0xfc. And we're just going to now loop through the remaining hex string, incrementing our index so that we can move along in our shellcode array. And we're going to keep running that same command. We're going to run stir toke s to trim off our next token, see if we were able to convert it successfully. If we weren't, then it's a null byte. And if we were, we're going to run stir to L, string to long to convert that to a long value and store it in our shellcode array. So let's take a look at how that looks. We run it, we get the output FC4883 E4 ending in FFD5. So it successfully converted our shellcode, our reversed hex string, back into shellcode bytes. So let's see if threat check thinks that there's anything wrong with that. No threat found. So now we're going to run each of these through VirusTotal. So we'll start out with reverse byte order. We'll tell VirusTotal that we're not actually robots. We'll see how this scored. We see it's already detected by at least one engine. While that's running, let's check another one. So now we're going to do the reverse byte with a XOR. And you can see I've already tested this. So we've got a result there. That was 7. 6 using just the reverse byte order ended up with a 6. Reverse byte XOR was 7. And if we try the reverse string, let's see how that one scores. We see that one scored a 31. So that one did not fool virus total engines at all. That is the worst one that we're going to see here, probably in this example. So using the reverse byte order scored a 7. Using reverse byte order with a XOR actually scored higher, and completely reversing the string scored a 31. So obviously not an ideal method for using to hide our shellcode. So with that, that wraps up this installment of Shellcode Obfuscation. I hope you enjoyed this installment. Stay tuned for the next one where we're going to look at even more obfuscation methods.